Before we kick off the official lesson, let's review something you should have learned last year in AP Calculus. We talked about rectangular and polar coordinates in R2 space. Now, R2 space is just the Cartesian plane. So we would say we could take a point, any point in a Cartesian plane, let's call it xy, and we can convert that to the polar system, which would be r comma theta. And of course, we learned that x was equal to r cosine of theta, y was equal to r sine of theta, and good old-fashioned x squared plus y squared equals r squared. That's the Pythagorean theorem. We could also note this relationship, that the tangent of theta would be y over x. We could also write this relationship, the cosine of theta is x over r. Now let's come over here. We'll do a quick Cartesian plane with the x and y axis. And this is a real simple review. So any point out in here, which traditionally we use rectangular coordinates, x comma y, r is the distance from the pole or origin out to the point. And so you can see that we create this right triangle where this is the x and this is the y, and that's where we get our relationships, that x is equal to r cosine of theta, theta of course being the angle rotated counterclockwise, starting with the x-axis and rotating counterclockwise. Now all the points in the Cartesian plane can be obtained if we say that r is positive and we restrict theta to be between 0 and 2 pi. We can still get all the points in the Cartesian plane if we make that restriction, and we're going to do that so that each point has a unique polar coordinate. Let's review some quadratic relationships in R2. The x squared plus y squared equals 1. You should all know that that makes an ellipse. How about x squared minus y squared equals 1? That should make it hyperbola. This should be review for you. Does anyone know what this quadratic relationship results in? Well, this has no shape. How about the next one? X squared plus y squared equals 0. That has a shape. It's a single point. It's the origin. And the last one? Do you know what that shape graphs as? It actually graphs as two intersecting lines. You end up with the absolute value of x equals the absolute value of y, and you get two intersecting lines. In this lesson, we're going to talk about how to write points in R3. Now, R3 refers to all of three-dimensional space. Rectangular coordinates are straightforward. X coordinate, y coordinate, z coordinate. And we're going to talk about how to convert that to what we'll say a cylindrical coordinate system, which goes r, comma, theta, comma, z, just as one example of a cylindrical coordinate system. The idea behind a cylindrical coordinate system is that every point can be thought of as some point along a circular cylinder. So if my Cartesian plane was here, the x-axis and the y-axis, and I wanted to obtain a point out here, well, I can do my traditional x, y, and then come up with a z. Or I can say, what is the point on the polar circle? And in this case, the polar circle is here. And then I'm going to go up z units. So the conversion there is real straightforward. X is equal to r cosine of theta. That's the x coordinate along the circle. Y equals r sine of theta, again along the circle. And then we'll just go up into the z plane, z units, up or down. The relationships we talked about earlier still exist. Tangent of theta is still x over y. The cosine of theta is still x over r. And of course the Pythagorean theorem. X squared plus y squared is still equal to r squared. R is going to be greater than or equal to 0, like we talked about just moments ago. And theta we will restrict between 0 and 2 pi. In this case, we can still obtain all the points in R3. Now we're going to work out example 1 and 2, and then we'll come back to work out the spherical coordinate system. Okay, in example 1, there are 2 points. One of the points is going to be 1, comma pi, comma e. Now that's in the form r, theta, and z. And we want to convert that to what we recognize as traditional rectangular coordinates. And what we do here is simply use our conversion formulas. X is equal to r cosine of theta, y is equal to r sine of theta, and z is equal to z. So this comes out to be cosine of pi, 1 times the cosine of pi, which is -1. This comes out to be 1 times the sine of pi, which is equal to 0. And z is equal to e. So that converts to go -1 on the x-axis, 0 on the y-axis, and up e units along the z-axis. The next cylindrical coordinate is 1, 3 pi over 2, 5, and we're going to convert that to rectangular. So x is going to be r cosine of theta, y is going to be r sine of theta, and z is going to equal z. And so what do we have? R, which is 1 times the cosine, 3 pi over 2, which equals 0. 1 times the sine of 3 pi over 2, and that's equal to -1, and z is equal to 5. So that cylindrical coordinate converts to 0, -1, 5. Now in example 2, I'm giving you the rectangular coordinate, and you're going to find the cylindrical coordinate. So this is the coordinate x, y, z. So we say x is 2 radical 3, y is going to be 2, and z is going to be -1. Now if we draw the Cartesian plane, so the z-axis is coming out at you, the positive z-axis is coming out at you, and this is our traditional. So we go over a positive 2 radical 3 units, and then we go up a positive 2 units, which gives us here, and then we actually go into the computer screen -1 units. All right, so in order to find r, that's just going to be the distance from the origin out to the point. So we're going to use Pythagorean theorem, and we'll say that r is the square root of x squared plus y squared, which is going to be the square root of 16, which comes out to be 4. Now we're going to find theta. I like to use the relationship with cosine. So we're going to say cosine theta, and I'm going to use a prime. I'll explain why I'm going to do that in just a moment. And that was the relationship x over r. So x is 2 radical 3, and r we computed to be 4. So that makes the cosine of theta prime radical 3 over 2, which makes theta prime equal to the inverse cosine of radical 3 over 2, which comes out to be pi over 6. Now the theta that we want to find is going to be equal to theta prime, which is equal to pi over 6. Now let's talk about theta prime. Okay, we will notice that we are in the first quadrant, this ordered pair again. We found this point here and then went into the page, but the traditional first, second, third, fourth quadrant were in the first quadrant, in which case the theta prime we find is equal to the theta that we want. Theta being the angle, again rotated, from the positive x-axis rotating counterclockwise. And you'll see in the next example why that is an important thing to at least consider. So just to summarize, xyz is going to convert to 4 as r, pi over 6 as theta, and -1 as z. R, theta, z. Next example, we're going to take 4, -3, 2, and we're going to convert that to cylindrical coordinates. Here our x is equal to 4, our y is equal to -3, and our z is equal to 2. I'll do that quick plotting of the Cartesian point, and then we'll decide whether that goes into the computer or out towards u. And so we go out 4 units, 1, 2, 3, 4. We go down 3 units, 1, 2, 3. That gives us this point here, and then we go away from the computer towards your eyes 2 units. You will notice, please, that this is in the 4th quadrant, and that's going to be important when we discuss our theta. So first off, r, the distance from the origin to the point, Pythagorean theorem, square root of x squared plus y squared. That's going to be the square root of 25, which is equal to 5. Now the cosine of theta prime is going to equal 4 over 5, and so theta prime is equal to the inverse cosine of 4/5. Now that value, because of the structure of the inverse cosine, that's actually giving you this angle here. That's theta prime, but that's not what we want. We want the angle that rotates from the positive x-axis counterclockwise all the way around to this point here. So we don't want theta prime when we're in the 4th quadrant. We want 2 pi minus theta prime. And so now our theta is going to be 2 pi minus theta prime, or simply 2 pi minus the inverse cosine of 4/5. And so the cylindrical coordinate is going to be 2 pi minus inverse cosine 4/5, comma 2. Here's a quick sketch of the inverse cosine function. We can input values between -1 and +1, and the output is going to be between 0, so the range is going to be between 0 and pi. So at best, the angle is going to give us is pi. So if we rotate, sorry, let me pick another color here. If we rotate, we can only get the angle between 0 and pi. So if we're in the 1st or 2nd quadrant, whatever theta prime comes out to be will also be our theta. But if we're in the 3rd or 4th quadrant, then we have to do 2 pi minus that in effort to get the theta that we want, which is these down here. Next, we're going to talk about the relationship between rectangular and what we will call spherical coordinates. Okay, let's draw a coordinate axis system just to give us an orientation of this. So here is the positive x-axis, here is the positive y-axis, and then going up is the positive z-axis. We're going to take points x, y, z, and we're going to convert them to rho, theta, phi. And so we need to explain what those items are. So if I take, actually, I'd like to talk about the phi first, because this one is sort of brand new. It's another angle. So if you were standing with your head going in the positive z direction, and you were standing on the Cartesian plane like this guy is doing here, and you were to fall from that, not moving your body, but fall straight down and then smack the Cartesian plane, that would be the angle of phi. That goes from the positive z down towards the Cartesian plane. So if you were doing that, and by the time you landed, so here this person now is smack laying on the Cartesian plane, that phi would equal pi over 2. Now, if they continue to fall through the floor, and by the time they were done falling, their feet were here and they were perfectly upside down with their head in the negative z, well, then they would have rotated phi equals pi units. Now, the theta is the traditional theta. That's starting with the positive x and rotating counterclockwise towards positive y, and that is our angle theta. Let's consider this point in space x, y, z. Now, the variable rho here, that's going to be the distance from the origin out to that point. So that's not r. R would be the distance from the origin along the Cartesian plane to a point out in space. But this is now from the origin out to the point in R3, anywhere in three-dimensional space. Now we're going to develop the relationship, the spherical coordinate relationship. Let's draw a point in three-dimensional space, which is here. Now this is really important that you try to visualize this. So what I'm going to do is I'm going to drop that point down onto the Cartesian plane. Okay, so now that point lies on the Cartesian plane. So we have a couple things that we know. We have the distance from the origin along the Cartesian plane out to the XY location, and that is what we call r. Then we have theta, and theta is this angle here rotating from positive x to positive y, and that is our theta. Now rho, as you recall, is from the origin out to the final point. Okay, so that is rho. Now to make sense of this, I'm going to draw some parallels. That distance here that we said was r, if I look at some perspective, this r here is the same distance as the r drawn below. So this is also equal to r. So you have this parallelogram. Let's trace this parallelogram. So that comes down like this, and then it goes out like this. That's equal to this value here, and so we have that. That's actually a rectangle. Okay, so back to this point here. This is the point in question. That goes up z units along the z-axis. Now, let's label the all-important phi. Okay, so I'm going to come up. Now, remember, phi starts with positive z and falls towards the Cartesian plane. So up here is our phi. That's that angle right here. And so now here we go. We know that x is always equal to r times the cosine of theta. But what we want to figure out is what r is in terms of phi so that we can get this conversion down. All right, so to see that better, let's draw the triangle. So this is the z, and then we have the r up at the top, which is in that green color. And then I'm going to draw the rho. Rho is this pink purplish color here. Rho, r, z. And then phi, of course, is this angle here. We can see that the cosine of phi is going to be z over rho, so that concludes that z is going to be rho times the cosine of phi. In a similar way, we can say that the sine of phi is equal to r over rho, and so we will say here that r is equal to rho times the sine of phi. And that's what we want for r. So I'm going to come over here and say rho sine phi. Now the y is always r times the sine of theta, and r we just said was rho sine phi, substituting that, times the sine of theta, and then we have the conversion for y. And now z, which is, we did that here already, which is going to be rho times the cosine of phi. Let's summarize this. X is going to be rho sine phi cosine theta. Y is going to be rho sine phi sine theta. Z is going to be rho times the cosine of phi. Now, x squared plus y squared plus z squared has to equal rho squared. That's like the three-dimensional version of the Pythagorean theorem. And so, of course, we would say rho is the square root of x squared plus y squared plus z squared. Then I will also say that the cosine of phi is equal to z over rho. I can also say that the cosine of theta is going to be x over rho sine phi. We are going to restrict rho to be greater than or equal to 0. The phi is going to be between 0 and pi. I don't need to go past pi. If you recall, I'll try to draw this again. Pick a different color, sorry here. So if this here is representing rho equals 0, and I fall down, now facing the absolute southern pole, so to speak, then I have rotated phi. Once I go past that rotation, I start to come back up again. And I don't need to go back up again because I can take care of that with a theta rotation. See, theta is going to take care of the circular rotation. And if I were, in fact, over here, theta would take care of that, and then I would fall down to that position. A little bit confusing. But that leads us to what theta. Theta, like before, is going to be between 0 and 2 pi. With these restrictions, we can still obtain every point in R3. If you picture the Earth on the coordinate axis system, as I've shown here, then the XY trace can be thought of as the equator. And the XZ trace can be thought of as the prime meridian. This helps us visualize 3D space in terms of northern hemisphere and southern hemisphere. Of course, in this model, the positive Z would be the North Pole, and the negative Z would be the South Pole. And we can also think of 3D space in terms of right hemisphere and left hemisphere. And so when theta is between 0 and pi, that's going to make us belong to the right hemisphere. And similarly, if theta is between pi and 2 pi, we are going to be in the left hemisphere. In terms of phi now, this portion, so the phi angle will drop to here, and so if phi is between 0 and pi over 2, well, then we're going to be in the northern hemisphere. But if phi is between pi over 2 and pi, then we're going to be in the southern hemisphere. Now, of course, if phi equals pi over 2, well, that would put us on the equator. And lastly, of course, let's say phi was equal to 0. Well, that would be the North Pole. Phi is equal to pi. That would be the South Pole. In example 3, we're going to go from spherical coordinates to rectangular coordinates. So here we have rho is equal to 5. We have theta is equal to pi over 2. And we have phi is equal to pi. And essentially all we need to do here is our conversions, which is rho sine phi cosine theta. You must have these committed to memory. And y is going to be rho sine phi sine theta. Z is rho cosine phi. And with a little bit of substitution, we realize that x is 0, y is 0, and z is negative 5, so we're on the South Pole here with ordered pair 0, 0, negative 5. Exercise 3 has another point that we want to convert, and this is going to be 4 pi over 3, 3 pi over 4. I think you could see this. This is going to take us in the right hemisphere, and this is going to take us in the southern hemisphere. And that can be confirmed here with our computations, which leads us to radical 2, radical 6, negative 2, radical 2 as our x, y, and z coordinates. And our last order of business here is to convert rectangular coordinates into spherical coordinates, x, y, and z. We're going to start off by first finding rho, which we talked about was the square root of x squared plus y squared plus z squared. So we have 0 plus 3 plus 1, and that gives us 2. So our rho is equal to 2. Next, I'm going to use cosine here to compute phi. And using that formula, it was z over rho, and so that's going to be 1 over 2. So now phi is going to equal the inverse cosine of 1/2, And these always work out because the inverse cosine is always between 0 and pi, so it's always going to give us what we want. We don't have to use a phi prime. And this is going to be pi over 3. All right. Now, the cosine of theta prime is going to equal x over rho sine phi, using that formula. Okay, so that's going to be 0 over, well, it doesn't quite matter now, but let's just be thorough, and that's going to come out to be 0. And so now theta prime is going to be the inverse cosine of 0, and that comes out to be pi over 2. And so now theta itself, see, x is 0, y is radical 3, so we're on the y-axis. So if you visualize that, you would say, oh, the theta that we desire actually is the same as our theta prime, which is pi over 2. And so that point converts to the point 2 pi over 2 pi over 3 rho theta phi. I'm going to skip to example D of example 4 and let you do B and C on your own, and I'll post solutions. So here we go. Rho is going to equal the square root of 1 plus 1 plus 6, and that, of course, is going to come out to be 2 radical 2. The cosine of phi is going to be negative radical 6 over 2 radical 2, and that comes out to be negative radical 3 over 2. Consequently, phi is going to be the inverse cosine of negative radical 3 over 2, and that, of course, is 5 pi over 6. Now we're going to find theta. Before I do that, I'm going to recognize here that negative 1 will put me in the third quadrant. So that lets me know automatically that my theta in the end will be 2 pi minus theta prime. So first let's find theta prime. So the cosine of theta prime is going to be negative 1 over 2 radical 2 times a half. That's going to simplify to be negative radical 2 over 2, and consequently theta prime is the inverse cosine of negative radical 2 over 2, which comes out to be 3 pi over 4. Great. And so now our theta is going to be 2 pi minus theta prime, which is 2 pi minus 3 pi over 4, and that's going to come out to be 5 pi over 4. And then I'll just finish off with writing the ordered pair. And finally, here are the answers to B and C.